squared. You remember that one? What? Yeah, decomposing body, decomposition. I'm not sure you would call body's decomposition. I guess you could make it a noun. That's true. We did decompositions last semester, but it was a little different context. Remember when we did decomposing a function? Okay, well, what's the opposite of decomposing? Composing. Wait, composition of functions. Hold on. What are compositions of functions? Or what are composite functions? Remember those guys? No? F of g of x, compositions of functions, fog, f little o g. It was this dude. Except instead of just having like a little o, we figured out that that little o is confusing. There was that nasty notation where a lot of you thought it was times and it wasn't. So I wrote it in the easier way, f of g of x, or maybe there was an f of a g of an h. There were inner functions, inner ones and outer ones, kind of like little Matryoshka dolls. You have like outer shells, but yet there might be something hidden inside, and there might be something hidden inside of that one, etc., etc. So decomposing was to take something that was all put together and break it apart, something that we've actually done a few times this year. And in that case, you could have had something like, I don't know, the square root of x squared plus 1 cubed minus 4. And we could have said, like, hey, let's decompose this guy. Let's decompose this guy. Let's break him down. There's all these functions that have been put together, and actually this one would be a really great f of g of h. This is a composition of functions. A lot of things have been put inside each other. What's a decomposition? Break it down. And we would say, who's h? Well, who's x? Well, there he is. Okay, that's boring. All right, fine. Who's around x? Who's h? Who's right around x? Yeah, x squared plus 1. Okay, if that's right around x, that must be h. What's around h? Who's g? Who's around this guy? X cubed minus 4. Now, that gets hard when you start saying x cubed, but x cubed minus 4. And then who's around g? Who's f? That's one way. There were multiple ways of doing that. But yeah, Nathaniel, good job. Decomposing, like a decomposing body, is breaking down into its elemental pieces. We did that with compositions of functions, and now it's time to do that with rational functions, which are fractions. So before we can ever do that, though, we have to actually divide when improper first, which, a quick reminder, I'm going to put it on the next page when we actually start taking notes on this. A quick reminder, when you take an improper fraction, a fraction is only improper if a polynomial will come out. Now, polynomial could just be a number like 1 or 3 or 5. It could just be a constant function. It could be like a 2x minus 4. It could be a line. It could be an x squared plus 5x plus 2. But some sort of polynomial can come out of that, and then there's like this little fraction remainder. That's the guy that we would do this whole process to. Anyway, reminding you a little bit about division when improper is possible. You'll get a polynomial. You'll get a remainder out. That remainder is who we break down. But all of this is how you break down. Start by factoring, and factors can look a couple different ways. Now, most of you are used to, when you have quadratics, you factor quadratics, but aren't we advanced enough in our math training that we know not all factors, not all quadratics have real factors, right? Can't you have a discriminant, which is the guy under the square root of the quadratic formula being a negative, so there are imaginary zeros? Isn't it possible that a quadratic doesn't have any, solutions to quadratics? Algebra 1. Oh my goodness, everything's coming together. Intercept form shows us the x-intercepts are the same thing as the zeros, the same thing as the solutions, but if a parabola never hits the x-axis, well, there won't be any. So we try to factor unless we can't. And if we can't, what's the snazzy word this says about a quadratic that can't be factored anymore? Irreducible. That's a good vocab term. But if it is reducible, we keep factoring. If it's not, oh well, it's stuck. One of the most common irreducible types of quadratics that you guys frequently, you guys meaning pre-cal and below, math students frequently mess up is something like this. What do you think he factors to be? What do you think some people make the mistake of thinking he factors to be? X plus 2 squared. Or x plus 2x minus 2. Or x minus 2 squared? Why are all of those wrong? What are the zeros? If the zeros lead to the factors and the factors lead to the zeros, what are the zeros? It's imaginary. Square root of a -4 doesn't work. There are no factors. What's the mistake people are making when they try to? They're saying, I can square root him. And they're doing like this weird like distributing of a square root. And then, I don't know. Anyway, I do, because the mistake happens all the time. But x squared plus a squared is an irreducible quadratic, impossible to be factored anymore. Well, while staying within the reals. So that once we factor all the way, we'll factor all the way to there if possible. And if not, okay, we might get stuck there. Now we have to look at these two different types of factors, or whatever factors we have, and say, all right, there are two different categories of partial fractions to set up. So check in. When we have a certain factor of a certain form, we make a certain type of partial fraction. Now, right now it's just a lot of words, and it's a lot of overwhelming words, which is why you guys go, you actually have to write it. So here, my summary, right? My summary. What does it mean to be improper? Because that's the very first step. And that's the very first step that leads us, when we have a numerator over denominator, if it's improper, we must divide first with the numerator going inside the box, denominator coming out, us trying to figure out some sort of polynomial, because if it's improper, a polynomial comes out, but also some sort of remainder. Now they use like N1s and D1s and all sorts of jazz, and okay, it's not bad, it's not awful. But I kind of like using letters that kind of signify what it is we're trying to do, like P for polynomial, R for remainder, whatever's left. But the biggest thing for you guys to realize is when to do the division process. And John's helped me out a lot today, so I'm not going to bug him. But I can ask him, like, hey, is it ever important to divide? To do polynomial division? And integrals, and his answer would still be yes. Think we're trying to break something complicated down into simpler pieces. Oh my goodness, how realistic and how practical is that in life? Taking something complicated, in our terms it's a rational function, but breaking it down into its simpler pieces. It's not what you always want to do. You don't always want your car like taken apart in your driveway. But if you need to find the problem, then you know how to work with cars. It's a good idea. And then you still need to drive somewhere. Well, I need it all put together sometimes too. So sometimes we need the whole thing all put together, common denominators. But sometimes it needs to get broken down and taken apart in order to actually be useful. I should probably think of another illustration besides a car. Not many of you take apart your cars. The mechanic does that. It all happens like behind closed doors and everything. What's something else that's really helpful? Sometimes put together, but sometimes pulled apart.
Legos.
Oh, nice. Nicely done. That's true. To understand the structure. Isn't that like a new reality TV show with Legos?
Lego
Is it a good one? I'm just saying. I saw someone's huge thing like go crashing down on a commercial, and I was like, I just got stressed out. Yeah, just even thinking about it. That helps. I was thinking Transformers, because sometimes you just want to be the cool little car, and then sometimes you want to be the big old monster. You can do that too. That's not really breaking down. Legos makes more sense. Anything else? The Lego reality TV show made me think of something like Cupcake Wars, or one of those other, like, was it HGTV, whatever that channel is that has all the cooking stuff. Sometimes you want everything all put together, like, I don't know, like a cake or like a pie, or what else do you put all the stuff into? Like a a pasta dish, but sometimes it's like, no, let's take the chocolate ice cream. That's good. I like it. Well, that's just me. Everything's better with Girl Scout cookies. Hit up Ariana. Long division, improper. What I need you guys to really make a point of as you're writing these things down and getting ready for me to fill in is this. What do I mean by degree? What's the degree of a polynomial going back to algebra 1? Basic. What's the degree of a polynomial? The power of x, but which power of x? You might have multiple. The highest power of x. Yeah, the highest power. Highest one wins. Not the coefficient, it's the degree, it's the exponent, it's the highest exponent of x. So when the highest exponent of x on the top is higher than, okay, that makes sense. Improper fraction, yeah, we did that. 13 over 5. Wait, sometimes 13/5 is the best way that I want this, but sometimes I want it broken down into its elemental pieces. Mixed numbers and improper fractions. Sorry, I tapped the board. Improper fractions are sometimes way easier to do math with, but sometimes I just need to know this is 2 and a little something to know how many I have. Anyway, it's really obvious when the top degree is higher, but the or equal to is the really tricky one, and it still tricks my kids in Calc AB and Calc BC. If the degrees aren't equal, division will make it easier. Factor, denominator, completely, I don't know, factor. I don't really have much to say about that. But the types of factors that you get puts you into 2 different categories. The types of factors that you get. So you're taking, well, if you needed to divide, you're taking r over d. If you're not needing to divide, you take the n over the d. So let's assume you divided. You're taking this r over d or n over d, either way. You're taking a fraction, trying to break it down. What you're going to do is put that r over d or n over d, take that fraction. But you're going to put not just the d, but you're going to put the d in the factored form. Okay, so you need to factor that denominator. Factor him completely as far as you can go. And once you have him factored completely, he is going to be the sum of all of his possible pieces. But you won't know what those pieces are yet. You're going to find them. And to find them, we have to at least tell ourselves that they're there and they need to be found. If I were to send you outside and be like, okay, go play hide and seek by yourself, your question should be, well, who am I looking for? Right? Scavenger hunt. I say, okay, go find it all. And you're like, well, what's the list of items I'm supposed to find? True? So this is kind of like setting up the list for yourself. The list is going to be 1 partial fraction for every factor, basically. Almost always true. 1 partial fraction for every factor. But there are 2 different types of factors that can occur. So if you have one of those like px plus q guys, then you're going to make him a fraction. You're going to be like, I need a constant to go on top. You don't know what he is yet, but you're at least telling yourself, I need to find that. I need to find the numerator guy. And you might have a different one. Struggle. Let's call that P1, Q1. There we go. P2, Q2. We'll just have, I don't know, you can have as many linear factors as you want. I don't know your polynomial, so I don't know the factors, so I don't know how many of these to make, which is why there's a dot, dot, dot. Here's where it gets a little dicey. There's one exception to this that makes it a little bit harder. But I'll talk about the exception because it could actually happen in either one. I'll talk about the exception about what additional partial fractions you would have to make in just a second. The other one that you might have is some sort of irreducible quadratic that you can't factor anymore. If that were the case, you would need to, let's assume you have like an A and a B. We'll go ahead and call this like CX plus D, but maybe you don't have those, so that would be AX plus B. Either way. He would need to be a part if he was a factor. If there was another one, God forbid, that would be horrible. Okay, not horrible, that's just being dramatic. But would not be fun if you had more than one of those. And some of you might be like, whatever, I'm just going to memorize. Okay, cool, we have to make these guys. And then you'll understand more when we do some examples. But some of you still want to have some semblance of understanding as to why it changes. Partial fractions are all supposed to be proper. And if they're proper, the degree of the numerator is less than the degree of the denominator. These are technically x sub zeros. They're 1 degree less. What's 1 degree less of a square? A linear. So I'm making partial fractions as proper fractions, where the degree of the top is 1 less than the degree of the bottom. So for a linear, 1 degree less is just a constant. For a quadratic, 1 degree less is a linear. It wouldn't have a quadratic up top, or else it should have been divided away up here because of the greater than or equal to. Same rationale why it wouldn't be a cubic or quartic. It would need to be something that's proper, that's less than a polynomial. Here's the exception. And it's not really an exception, it's just like something for further consideration. I'm going to throw it in right here. What if, bless you, we have repeated factors? What I mean by repeated is some sort of, I don't know, let's just do like a basic one. Like x plus a. What if it's cubed? So it's linear. It's 1x plus a. It's a linear factor, but it's cubed to the power of 3. I want you guys to think about this. I don't know what the numerator is. I'm just going to call it n. I don't know. It's something. If I was trying to split this up into its partial fractions, I would need 3. It's a cubic. I would need 3 different partial fractions. But the problem is they all have the exact same denominator. Like, that's dumb. Yeah, that could be multiplied by x plus a squared to become a part of the cube. But I'm not going to make them the exact same. I'm going to say, well, it could have been this guy to the 1, it could have been this guy to the 2, or it could have been this guy to the 3. And I would have to make partial fractions for as many, counting up to as many as I have repeated factors. And here's the reason why. When you have repeated factors, you're going to have to make a partial fraction for each possible power. And the reason why I'm saying each possible power is, as you guys yesterday in the T proof were like, we know how to do this side. Awesome. Common denominators. Could this guy have a common denominator to get there? Yep. But could this guy have gotten a common denominator to get there? Yes. But could this guy have, well, he was already good to go in. Any of these could have joined to have been or to have made that. So I have to allow for the possibility that there might be something there. Any of them could have joined, so I have to allow for the possibility. So if you have repeated factors, that was just the why. The how is just to form a partial fraction for each possible power. So guys, how many of these would I have? This was to the 10th. Don't worry, it won't be. But how many would I have? If it was to the 10th power instead of cubed. 10. Yeah, because the first power, second power, third power, fourth power, all the way up to the 10th power. Super annoying. You won't have to see one that bad, but just kind of letting you guys know what to be looking for. Once again, like the scavenger hunt, if you don't have a list and know what to look for, how are you going to get there? To let you know, just real quick, I'm going to be super honest with you up front. There is one shortcut to this entire section, but listen, it sadly only works for the easiest types. I mean, it's nice that there's a shortcut, but it sadly only works for the easiest types. In algebra, think factoring. Oh, it's great if it works. If it doesn't, we need quadratic formula. It's kind of similar to that. So even though in Algebra 1 factoring is so important, we teach it first, there's a whole chapter of it first, before you ever see the quadratic formula, you learn factoring and try to get really good at it, because if you can do it, it's awesome. I'm not going to show you the shortcut first, because it really is the exception in Precalc. Cool thing is in calculus is they pretty much only give you ones where you can use the shortcut, because they're giving you simple-ish ones, because the math you're doing is harder. So they give you like simple Precalc, and then you have to do the harder calculus. But for you guys, we're just learning partial fractions. If I only show you the shortcut, you might turn into honors where they try to do the shortcut for everything and then they miss most of the problems because they never learned how to do the long way. Let's do the long way first and just realize there is a shortcut coming, but it's only for the easiest types. And I'm so sorry because we want shortcuts for the hard types, not the easy types. Oh, there's the shortcut, but we're not doing it first. We're doing it the normal way. So, beep, beep. This is one of the easiest possible partial fractions you could ever see. It's one of the easiest partial fractions. Wait a minute, isn't this the guy who was in the T proof? We already know what the answer is. But only because I showed it to you. Remember, you didn't know how to do the other side. So let's figure out how to do the other side. The other side says, aka working with this and trying to break it apart says, step one. Well, you guys tell me. I'm tired of talking. What's step one? Okay. Is it improper? Yes or no? Why not? Yeah, you see it? Denominator on top has a degree of 1, on bottom has a degree of 2. Is the top stronger than the bottom? No. Is it equal to the bottom? No. Okay. So now what do we do? Step 2. Factor. All right, cool kids. Show off your factoring skills. What's this end up being? X minus 3 and plus 2. Woo! Are we okay? My quiet ones, you knew it. It was too easy. You didn't want to say it, right? I hate forgetting it now. Okay, so, coming back. There it is. We write that x plus 7 on top because I need to know what I'm trying to break down. But I want the denominator in the simplest form because if I can get it factored, don't I know how to start setting up what I'm looking for? Wait, why did it let me write 2? Lots of ways of thinking about it. It's only a square. There's only going to be 2. There are only 2 factors. There are only going to be 2. Think about the Lego example. Couldn't most of you look at a structure and kind of figure out what some of the pieces are, right? What could join together to make this guy? Wouldn't he have some pieces? Couldn't he have some pieces? Right? What am I doing? I'm doing step number 3 and 4. I'm looking at my factors and I'm forming partial fractions based on the factors that I see. Now hold on. So far, we know this, we know this, we know this, we know this, we know this. What don't we know? Numerators. Without cheating and being like, oh, she already gave it to us, huh? So what did I say? We're going to be putting above any sort of linear factor as our unknown because we have to keep it proper. And if this is a linear, we have to go down a degree. Variable, and not like a linear one, just a constant. That's it. A and B. We don't know them, we need them. Yes, I know that you know who they could be. The T proof, we're starting on the left-hand side, trying to get all the way there. Now, that huge old table of stuff you guys didn't want to write down, it was just getting you here. It was just setting up the problem. Nothing about how to solve. So if I were you, can I write in a different color the steps as we do the steps? The steps to solve, because we need to know A, we need to know B. Have you learned anything from these issues? If you see a nasty equation, a nasty expression with division, as long as it's not a T proof where you're stuck to one side, if you're allowed to work back and forth, what's the most logical step forward? Huh? When you have fractions, you don't like them, you have an equation, you're allowed to work back and forth. What's the most natural step forward?
With like times.
Yes. But not just that. Let's times everything. Why? I don't like fractions, don't you? Dislike fractions too. Can we just multiply that on the other side? Let's get rid of all of our fractions. When we multiply, he's gone, and I just have x plus 7. Well, at least it looks better than algebra. What I do to one side. Do to the other. I'm just curious the way your brain would do it to the other. Ready, set, go. What you do to one side, do to the other. You have an addition. Would you do addition? Come on, it's algebra. I'm multiplying this to the other side, right? Do it to the other side. Right now it's unbalanced. Imbalanced? Balance has been thrown off. thinking about it? Yes. Why did I say there's addition? FOIL, except I would keep this as a big old lump. I'm really hoping to not have to FOIL. Because I just undid the foiling, right? I just factored. I'm trying to think of this as like as a big old lump if I can. Getting rid of it, getting rid of it. Let's just use the word distribute, right? Some of you mental mathers would be able to get here naturally. If you're like, oh yeah, makes sense. Cool, do that every time. Move it to the other side. Reduce whichever ones don't apply. Keep whichever ones are stuck. Or I should say reduce whichever ones are able to reduce. Keep whichever ones don't. For those of you that you're like, you probably need to write it next to both in distributing. Technically, it was out here. You distribute it in, it goes to both. And then we have to think individually, just old school, multiplying fractions. If what's on top and what's on bottom matches, they reduce and we keep what's left. Keep what's left. So I'm multiplying to the other side, I'm distributing. Some of you are already starting to see patterns. If these are always coming from this, when I multiply this on the other side, something will always reduce and something will always be left. Something will always reduce and something will always be left. Now, to answer how to solve this, I need to actually draw your attention or remind you of when we were doing complex numbers. Not in trig form, not the nasty like cosine theta plus I sine theta with r, but the good old school complex numbers. What if I was to tell you something like, hey, the complex number is 3 minus 2i? But what if I was to give you something like 2a plus 3bi? And I told you to solve for a and solve for b. You guys hated this in homework, but it was actually kind of preparing you for today. How is it possible, with all the work that we've just done in the systems of equations, 2 unknowns, 2 equations, 3 unknowns, 3 equations, how can you have 2 unknowns and 1 equation and still solve it? So it's the very same, oh dear, who's outside? The very same equation, or the very same process we need over here. How do we solve for a? What do we compare him to? Because, isn't he real and he real? I say you're real, okay, cool. So 2a has to make 3, which means a is going to be 3 halves. And what's 3b need to equal? -2, because that's imaginary and that's imaginary. Even though there is one equation, there are different types of variables, different types of quantities, and I can match them up. So I can say 3b is equal to -2. AKA b is equal to -2/3. This was harder than any of the ones you saw back in complex numbers, but the same idea is there. One equation, 2 unknowns. It's impossible unless there are different types of quantities that we can match up. How does that apply to here? What's one type of quantity that we have? X terms. What's the other type of quantity that we have? Constants. Are X terms and constants separate? Yes. Always separate? Yes. Can they ever be combined? No, they're not like terms. So guess what's over here? X terms and constants and X terms and oh my goodness. Hold on, I can't see it all. It's too confusing. I need to distribute everything out. Multiply my A's, multiply my B's. Oh, but now I can see them, can't you? Don't I have X terms? Don't I have constants? Let's get all the yellows, let's get all the purples, and let's see what we have. So, all the purples, we have 1x is equal to ax plus bx. X terms unite. The X terms had to make X terms. And why I put a 1? Because any understood coefficient is 1. Constants, unite. 7 had to come from 2a minus 3b. Ooh, this looks almost like a system, except that gnarly little x dude's in my way. What can we do with the little gnarly x dude? Can't we just say something like, oh, I don't know, GCF, let's factor out the x, and let's say, we don't really care about you because we care about your coefficients? I mean, we do. It was important to know that the x was there. But really, I just care about the 1 equals a plus b, the coefficients combining to make the coefficient of 1. So now what? Why is this in chapter 7? What's the technical way to solve? Set up a system of equations and go. You see it? It's a lot like this old problem that you didn't like a while ago. We introduced it way back when we did complex numbers, when factoring polynomials in chapter 2. Let's come back to focus here because we have to think of a similar idea. Some of you would be like, 1 equation, 2 unknowns, 3 unknowns. It's impossible. Think outside the box. You got x terms, group them. You got constants, group them. The x terms, the coefficients, take the coefficient, get rid of the x, and now all of a sudden we have a system. And how do you solve a system? Well, you're welcome. It's your choice. What you guys want to do? Row echelon form, substitution, elimination? Elimination. So then let's multiply this guy by what? A negative 2? All of our brains think alike. So negative 2a plus 2a will end up being 0. Danger, danger, but you guys are double checking me. Negative 2b minus 3b is negative 5b. And then negative 2 plus 7 is 5. Does b equal negative 1? If b equals negative 1, can I substitute back in? A plus negative 1 is 1, so a add the 1 equals 2. And can we go back to the very beginning of this page? And can we say, wait a minute, we were trying to break him down into, what were you looking for? Oh yeah, this and this, and oh yeah, we were missing A and B, but oh look, we found A and B. What's our final answer? You now know how to start from the other side of the You now know how to start from the other side of the equation. Now guys, I could just be like, you know what, right now, let's just go talk about a trick, because the trick is cool, the trick is fun, the trick is awesome. And I'm going to show you the trick, but I'd rather first at least have you set up a different type of problem that's not quite so easy. An improper one would be a great one to do, but that's going to take time to do long division. Can we do this one instead? Let's do this one instead. I'm going to come back to the thumb trick in just a second. If you guys want, you can just literally write down thumb trick, or you can write down Oliver Heaviside cover-up method if you want to be super snazzy. Oliver Heaviside, actual guy. Why this is named after him, I don't honestly know. Ironically, he was quite skinny. But either way, Oliver Heaviside cover-up method or the thumb trick method, we'll come back to it. Skip like 2 lines. All I need is 2 lines. But I want to make sure that you guys have the idea of at least starting these problems. And technically, what I just showed you will let you solve anything that you come up against with partial fractions, as long as you remember to divide first if it's improper. I just want to show you what happens if things get a little funny. And how does this same procedure apply? Proper or improper? Proper because top degree is 2, bottom degree is, if it was a 3, I would divide. If the top was a 4, I would divide. But nope, top is less than, so it's proper. So I'm going to go ahead and set up my first step, just like I did over here. Oh, but wait a minute, what did we do first? Factor. So hold on, take this guy just for a second and factor him. Common x, yeah? Okay, but, ooh, what's left? Why did I give you that as an example earlier? There it is. Can you factor him? The answer is no, but the question is, does your brain think it can? irreducible quadratic, I'm stuck with it. Oh well, it is what it is. But what did we write in our notes? What kind of numerator do we put above a linear? Check it over there. What kind of numerator do we put? Just A, whatever. B, a C, a D. I'm going to start with A. But what do we put above a quadratic? Yeah, go to the next letter in the alphabet. Sure, B, but make sure you have an X plus C. This is still proper. He's one less than. We have to account for as much as could be up there. Okay, Vanessa, you ready? I need you. What do we do next? We have the empty fractions. How do we get rid of them? Yeah, let's multiply. Why? Can anyone just answer? Did you see it over here? Why am I going to always multiply by this denominator? He's the only one that's going to be able to cancel everything out. He's the biggest one, so he has the highest likelihood, and if you guys understand those came from there, he's going to be the one that's not only going to cancel over here on the left, he's also going to take away stuff on the right. But as I start doing this, some of you that followed my mental math last time, just double checking that you can do this without showing too much work. What's A going to be multiplied by? X squared plus 4. What's bx plus c going to be multiplied by? Pause and put those bx plus c in parentheses. Times x. And for those of you that are like, I don't know how they did that, remember, what we do on one side, we do on the other, and that addition says we have to distribute. So multiplying the x and the x squared plus 4, the x's reduce, the other guy's left. This time, the x squared plus 4 will reduce. Oh, I'm sorry, guys, that totally did not fit in well, but that x is left. I'm going to grab out my yellow. It's great. I'm going to grab out my purple. It's great. I'm going to go find a random other color. Sure, why not pink? Why am I doing 3 colors now? I have 3 types of terms, right? I have an x squared, I have an x, and I have a constant term. What does that mean about how many equations I'm going to have? How many unknowns I have? How do I see it? I multiply it. And I say, oh, there's an x squared. Oh, there's a non-x. Oh, there's a x squared. And oh, there's a x. So who do I have? Well, I have these pink guys, which is going to, if you guys realize that x's really don't matter, it's just the coefficients that matter, maybe you can pretty quickly say, oh, from pink I get a plus b. Those guys combined had to make 3. You understand the idea? Wait a minute. C had to make 4. Ha! I know one. C had to make 4. He was the only extra. Hey, speaking of knowing one, what else do I know? 4a had to make 4. Nice. Let's be humans and be creative and say we already know an answer. Let's forget setting up the system. We know A. We know C. We can plug in and find B. Now, what's good and bad about what just happened? It was fast, it was easy, and it could be a lot harder. Because depending on what you have, you could have had multiple x squareds, multiple x's, multiple constants, 3 equations, 3 unknowns. We know not all 3 equations, 3 unknowns are this easy with substituting. We did a whole section 7.3 A and B on it, right? The nice thing is, some of them might be this straightforward. Wait, what was the point? Oh, scavenger hunt. This is what we were trying to find, and what do we now know? A over x, 1 over x. Bx plus c, 2x plus 4. If you guys ever want to check, don't you just have to do common denominators, pretend you're on the other side of the t-proof, and see if it matches? Do you see how the procedure is the same? Now, 3 colors instead of 2. I get it, but there were 3 different types of terms. The system is the same. Just a few of you heard the warning about, like, A, B, C, like X, Y, Z, 3 equations, 3 unknowns. There is a trick. So as we end class today, the trick wouldn't necessarily help in this problem at all, but the idea of the trick can be used in similar problems to that one to get us faster, closer to an answer if it were to be harder. So let me show you the trick of this one. The trick, the thumb trick, the Oliver Heaviside cover-up method only works in nice, easy ones like this. No irreducible quadratics, no bx plus c's, and no, to be honest, one more thing, no repeated factors either. It only works for this guy, not for that one, not for that one. But it gives us an idea that we'll look at tomorrow when the problem does get really messy about something else that we can use as a trick. So, same problem as, different problem. Different problem, and we'll use it for that one. Oliver Heaviside cover-up method says, start the exact same way. Start the exact same way. Have our x minus 2. Oh, do the factoring. You guys have x plus 3, x plus 1. Go straight to the answer. Only works for easy, non-repeated linear factors. I'm going to cover up a factor, and when I cover up a factor, you're going to tell me what the 0 is. And we're going to plug it in whatever remaining x spots are there. Okay, I'm covering up x plus 3. What's my 0? Negative 3. Oh, okay, so negative 3 plus negative 2 all over negative 3 plus 1. I'm covering up a factor. Give me the 0. Negative 1. Negative 1 minus 2 all over negative 1 plus 3. Negative 3 plus negative 2 is negative 5. Negative 5 over negative 2, I get 5 halves. And I get negative 3 over 2. Negative 3 halves. The book would write it a little bit weirder. They'd probably put like a 1/2 in front. And they would do something like this. Wait a minute. But does this work? Check it. What if I was to come over here and cover up an x minus 3? What would we plug in? 3. What's 3 plus 7 all over 3 plus 2? By the way, I'm putting this on top of the one I'm covering. Isn't that 10 over 5, which is 2? That was the answer. What's negative 2 plus 7 all over negative 2 minus 3? That's 5 over negative 5. That's negative 1. That was the answer. Woo! I like the trick, but only for the easy ones. That's all right. You get to a hard one, you can use the trick to kind of tell us another way to go about it. I'll see you guys later. So, BC kids, you in the fun for today. All right, guys. So we're not until Thursday. Please.